Great. Excellent. Okay. Exactly, Sebastian. So when you are ready, please start.
Okay, very good. Yeah. So yeah, I decided I want to go through this here really. I mean, some decent pace, and if we don't get to these measurements, that's fine. Yeah, so
that's great. It's great. It has been great.
Yeah. It's I would love to report it, but it's also anyways. So we were thinking about symmetries in this Keldysh formulation. And we were discussing the differences between strong and weak symmetries or their implications. And in particular, we figured out that the strong symmetries are associated to conservation laws. Yeah? While the weak symmetries, they are associated to spontaneous symmetry breaking and give rise, if these are spontaneously broken, to Goldstone laws. Now I want to complete the confusion and tell you that these strong symmetries easily get spontaneously broken as well. Yeah? But that has no, no fundamental new ingredients. Yeah? It's, however, very important to track this through the calculations. Yeah? So, and that will eventually explain us, yeah, doing this very carefully, how to obtain the correct response on top of these dissipative topological insulators. So we start now from this model M2, where we said, okay, this is the one with conservation laws, yeah, with particle
number. I think you did not share yet your screen.
You are trying to share? Oh, yes, you have not.
Yeah.
Okay.
Thank you.
Yeah, I was starting to write, but not much has happened. So, should share now. Yeah, okay. I started to write something. So we were looking at this model M2, which is defined with these Lindblad operators, which are just reshuffling the superposition of a particle, but not exchanging it with a bath. Yeah? And this is now an interacting problem. Yeah, we have terms of this L-dagger L type, for example, and they are quartic in these original operators. Maybe I put this formula still here. L1, L2, yeah, obtains by some unitary transformation from the original canonical annihilation operators psi1, psi2, and that's some 2x2 unitary transformation. Mm-hmm. Okay, so so we don't want to deal with this complicated interacting problem. So, and we know the dark state of it. Yeah, so we can do some approximation, some what is called self-consistent Born approximation. It is essentially taking these operators here and doing so a Hartree-Fock approximation to them. So we contract pairs of operators with each other. Yeah? And for example, this contraction here gives me just the mean particle number in the problem. Yeah? While a contraction, for example, of L1 dagger psi alpha, that always evaluates to 0, because this operator here acts on dark state which is annihilated. Yeah? So these contractions vanish. And when we do this Hartree-Fock approximation, we get essentially out this result here. The original interacting Lindblad operators are replaced by linear Lindblad operators, and the original coupling constant that stands in this interacting Lindbladian dynamics is essentially renormalized or rescaled with just the average filling of the problem. Yeah? So we can actually drastically, in the upshot, by this mean field theory, by this mean field contraction, where essentially, yeah, so we execute these contractions, we can go from an interacting model to a quadratic model, yeah, which is only defined with linear Lindblad operators. Okay, for this model, Yeah, the one important point is that it no longer manifestly has this strong U1 quantum symmetry. Yeah? So where is this physically coming from? Well, these contractions, they come from terms that on the original Lindblad equation, they look like that. So this term here is, for example, L1 psi dagger, or L1 dagger psi 1. Yeah. And when we do this contraction, so we are essentially taking a trace over these operators here and stand what stays, so that they go into a density. Yeah, so that's the psi dagger, the contraction psi dagger psi. And these two guys, they still stand in the master equation. So that's this replacement. Yeah, and that, of course, looks as if there is no particle number conservation anymore. But what really happened physically is that particle number is just transferred, just propagated through the system itself. Yeah? So we don't exchange really with the outer world. Here we have an instance in this dissipative evolution of a system acting as its own path for particle number. Yeah? And that's why then we can get an effective dynamics which looks like non-particle number non-conserving, but originates actually from this particle number conserving microscopic theory. Yeah? And so when we compute, for example, the single particle Green's function for this problem, it takes this interesting structure. So here is again this Keldysh Green's function. Here is this retarded response function. We have in this model a gap in the spectrum. So this retarded Green's function here it looks like that. This function as gamma of Q looks maybe like that as a function of Q. Yeah. So we use a Brion zone. We're working on a lattice, and there is a smallest damping rate in this problem, which is this quantity here. Yeah. And so there is a dissipative gap in the problem that maybe answers the question that was raised previously. Then we see also, and that's an interesting alert for this non-Hermitian topology discussion here, because this spectral Green's function here does not show anything topological at all. It's just a unit matrix in this span space, and the unit matrix cannot host any interesting topology. Yeah? Rather, what it turns out that the interesting topology here is in this occupation Green's function. Yeah? Namely, here we have this object that defined so that you can read as a Hamiltonian, and this object here hosts the interesting topology of this problem. So, but now what we have to answer is
one question: is this the gap that you are writing there requires the symmetry breaking? I mean, if you require to have this replacement with C numbers of the phi in order to get the gap?
This C number replacement, you mean?
Yes. Mm-hmm.
Yeah. I mean, in the origin, so a gap is usually thought of as a property in the single particle spectral properties. Yeah? Mm-hmm. And we start with an interacting problem, and actually no so to say no terms, so no quadratic terms to begin with. So in that sense, in that strict sense, yeah, so one would say the gap is zero, but it's of course a fake, yeah, because you did not yet consider the physics of this problem and mm-hmm. realize that actually because you know this dark state exactly and you can do this mean field decoupling, and therefore it turns out that there's a gap in the single particle damping spectrum, if you like. Yeah, so that's a good remark. Yeah. Okay, good. So what we learn, yeah, so this model M2 reduces to model M1. We have said in the model M1 there is actually no conservation law. So how can this be and that is now physically understood as a spontaneous breaking of this strong quantum symmetry. And I now want to convince you that the spontaneous breaking of this U1 quantum symmetry actually is not something that acts against the quantization of responses, as one would maybe naively suspect. Okay, so this I want to drop. And so here is the outline of this discussion. Yeah. So the full problem that we started from definitely knows about the number conservation that the problem has. It's only masked by this mean field theory. And if you do the order of approximation in the right way, then you can still somehow save the features of this underlying exact and actually particle number conserving theory. So in more detail, what we have to do to compute the response to electromagnetic fields, the procedure is such that we first need to couple to the response field, and then we do the approximation, this mean field approximation. And then in this approximated theory, we can then do the low energy calculation. That will give us the response to the electromagnetic field, which demonstrates in turn the topological character of the underlying state of the system. Okay, so and now we go into this construction. So we want to construct the response to external gauge field, external electromagnetic fields, and how this is done in the spirit of the minimal coupling prescription that you probably did in your quantum mechanics course. We promote the global symmetry, and now we are really speaking of the exact U1 classical times U1 quantum symmetry. We promote it to a local symmetry, and to do this, we have to introduce what is called this covariant derivative. Yeah? So whenever we have in our problem a kind of derivative operator acting on our fields, and again, we have to be now accurate with plus and minus fields on each of the contours, then we have to introduce a gauge field which compensates for the transformation with chi plus minus of t and x, acting on psi plus minus fields of t and x. Yeah. So if we have this covariant derivative and the gauge field transforms as the mu chi, then this covariant derivative, as usually, is, so to say, a right gauge invariant object. So that's the idea of minimal coupling. The only thing that we really have to do now, really accurately, is to do this in a contour resolved fashion. Okay. So that means now that our Lindblad operators will carry this gauge field with them, because these L1 operators, they are not completely local. Rather, this matrix here has components with which go linearly in Q, for example. So the transformation between the canonical operators that are acting on the lattice and these Lindblad operators here that are pushing us into the non-trivial dark state, that is mediated by some momentum-dependent transformation, unitary transformation. Okay, and therefore, because these guys here depend on Q, they will, after this minimal coupling, they will also depend on A, and now on A plus minus, depending on where they sit on the Keldysh contour. And if we then want to compute how is the dependence of these Lindblad operators on the gauge field, well, we do just this thing here. We look at L in the presence, or the full one in the presence of the A field is this transformation Q, and that's now Q plus A or plus or minus. And we can, if we are only interested in the long wavelength response, we can approximate that by V of Q plus and then D Qi V times AI plus minus field. And if we want this to appear in, so here is still the psi standing times psi, then this will take the form here are the brackets. This is the original LQ from this term here plus dQIV times, and now I insert here V minus 1 times V to make these, bring these here together into an L, yeah, by this definition here, V minus 1 LQ. Yeah, and that's exactly what stands here. So, and here, and times AI, and plus minus. Yeah, so here I missed the plus minus. Yeah, so here you can see how these Lindblad operators actually couple to the gauge field. Yeah. And if you look at that, up to some unimportant prefactor here, this object here is actually really a Barry connection in momentum space here. Yeah. So that's really how the topology enters into the Lindblad operators. Yeah? This U transformation or this V transformation is really the basis change from the original lattice operators into the eigen operators of the system. And these matrices, they encode the topology of the problem, okay, in terms of this Barry connection. Okay, so now we get, in principle, very complicated operators here, but within the mean field approximation, yeah, this is essentially our coupling of the Lindblad operators to the gauge field. So we get this here is a gauge field line AI, and this here describes fermions L dagger. And there's also, I mean, if you go to L dagger L, from this term, there's also two fields possible that can enter this vortex. Okay, and now comes the okay. What have we done so far? Yeah, we have now worked on the microphysics problem here, and we have derived, so to say, the coupling of the gauge fields A to the matter degrees of freedom L dagger L. Yeah, so that was this term that we said is one gauge field and two fermion fields going in and out. Okay. Now what we want to do, we have seen that these fermion fields, they are gapped. Yeah? So they feature this dissipative gap. And what one then tries as a physicist is to move to the long wavelength action by integrating out essentially the high energy physics of the problem, which is encoded in the degrees of freedom that are, so to say, exhibited to this dissipative gap, yeah, a big energy scale. So whenever we are interested at frequency scales, where here we have the dissipative gap, we call it with m square, and whenever we are interested in long wavelength scales or low frequency scales, which are much smaller than this dissipative gap, we can really just integrate out these fermionic degrees of freedom to produce an effective long wavelength action for the gauge fields alone. So again, this is nothing that is specific to equilibrium or non-equilibrium. That's just a matter of looking at scales in the problem, and we, having identified this dissipative gap for the fermion degrees of freedom, we can now proceed and integrate them out. Yeah? And what this will give us is then a partition function, which is only formulated in terms of gauge fields. So here is the result, yeah, the structural result. It will be some polynomial, yeah, in the gauge fields, and the coefficients that enter this gauge field action, this is essentially incorporating the effects of the microscopic fermionic constituents. Okay, and when you go through this program for this problem here, then, for example, this term here gives us this contribution. So here you can see this operator. So this x1 is something like that. There's one gauge field sitting here, and it has two fermion lines, yeah, and from this here another one. And by doing this average here, I'm doing nothing but essentially contracting these lines, and that gives me these diagrammatic processes here, which then encode these structure constants that are in this problem. Okay, that's maybe quite technical, but the upshot of this construction is this. Yeah? So when you do this calculation, we find this result here. Yeah? So we, first of all, we can represent this information here in terms of the microscopic fermion dynamics, and it gives us this expression here, where as a result of the calculation, we really find that this coefficient here is properly quantized and reflects really the Chern number of this, the underlying state. Yeah. So the upshot of this construction is this here. We get a quantized response of the system, which is purely reversible. Yeah? So it's the outcome of the calculation. Yeah? So the effective gauge theory is not at all dissipative or anything. It's really a reversible action of gauge fields, which you cannot distinguish by any means from the response of a Hamiltonian ground state system. Yeah? So that is the take-home message here. Very different from the from this system that we looked at in the beginning, namely this damped harmonic oscillator, where there was a huge difference between a unitary dynamics acting on this system as the response is concerned, and a dissipative system. Here we find somehow the opposite phenomenon. Yeah? Although the dissipative or the Hamiltonian dynamics acting on these states is vastly different in equilibrium and in this Lindblad case, we get exactly the same and quantized topological response sitting on it. In one line, topology wins over dissipation, if you like. Yeah, so, or over the actual dynamics in the problem. There's a question by Grace.
Yeah, so just in the diagram, could you explain like what these like half dashed, half solid lines are? And
you mean the shading?
Yeah, like what are the...
Yeah, I realize it. So I realize this now. So if you plot it like that, yeah, what you mean? So there is Green's functions. I can have this. Let me see. We can have this psi classical, psi quantum dagger, yeah, and we can have psi. I have these indices downstairs. Quantum and C, yeah. This kind of Green's function, I want to represent it with such a line, yeah. And this Green's function, I want to represent it with a, I mean, somehow just to graphically distinguish it, I want to represent it in this way. So what this tells us here is that there's this retarded response Green's function and range. Yeah.
Okay, got it.
So it's not really nicely done. It's not obvious from what stands here. But I think really beyond the concrete calculation, what is an interesting point is that there is this reversible and really just topological gauge response sitting on top of the of this purely dissipative insulating system. So that's the take-home message.
So Sebastian, but this topological response is associated with the strong symmetry. So any system that has a strong symmetry also obeys this topological response, or is just in addition to the strong symmetry?
No, you can say it like that. The strong symmetry is a prerequisite, yeah, so that at all we can compute such a response. Yeah. So let me, more physically speaking, without a particle number conservation, you don't have you cannot couple to gauge fields in the way you're used to. Yeah?
Okay.
So then you get no conservation law, and you don't get a gapless response, yeah? As we get it here. Yeah?
Okay.
So the strong quantum symmetry is, so to say, the line one necessary condition to obtain a quantized response. And then the question is, of course, yeah, quantized can also mean theta is 0. Yeah? So that's the trivial quantized response. Yeah? So then in that case, there's actually no topological response in the problem, but it's quantized. The question is, the more interesting is, of course, when you have really a Chern insulating state, yeah, and this theta is actually quantized to a finite value. Yeah? But yeah, that's an important point. Yeah? You need really these two, the strong symmetry in order to have a quantized response in the problem. Yeah? So in other words, yeah, particle number conservation is a prerequisite for having a topologically non-trivial response. Yeah?
Perfect.
So can I follow up on that question? So I mean, to understand, I mean, you started with the Chern insulator, you added dissipation, you started with Chern insulator, Chern number equal to -1, you added dissipation, and you end up with again Chern number -1 in a dissipative regime, right? So and you said that the topology wins over the dissipation. Is it like a general statement for any strong symmetry case, or always topology wins over dissipation? That's the question.
You are asking for what are the prerequisites for this construction to work, right? Eventually, you're asking, yeah. So you're asking, so to say, what are really the ingredients for this construction? Yeah. And in fact, the answer is, yeah. So the prerequisite is indeed particle number conservation. Yeah. It is particle number quantization. Yeah. That guarantees actually really the quantizedness of this, and you need the state to be pure. So these three are the three ingredients. Yeah, so I think I don't make it so, but you can rederive these results really just from symmetry considerations, and the three ingredients are particle number conservation, quantization, and the purity of the state.
So, but okay, I guess my question is, the final equation that you just show, it's essentially integration of the Berry curvature, right?
Right. Yeah.
So if I start a system that doesn't necessarily Chern number, it's a invariant. It's a different invariant has it. Am I always gonna get again semi-invariant to be quantized in the dissipative regime?
I mean, you're asking exactly. So you could ask for this model M1 without particle number conservation. Yeah. Let me answer like this. You can define a Chern number for this problem, no problem, yeah? Because you can just you can compute it. Yeah, you take your covariance matrix, or you construct just this Chern number integral, and you get a finite value. But that's a different story to asking, does it have a quantized response? Yeah, when I hit this system with gauge fields, and then the answer will no, that will not be quantized. Although you can define for the state a Chern number. That's really the upshot of this construction. Yeah? So, or that's what we learn. Yeah? Conservation laws are crucial to have really physically quantized responses. Yeah? So you could see it even very, I mean, formally you can look at it like that. Yeah? If you only have U1 cross U quantum, yeah, and we understand now that we promote the symmetry generators to local generators, and those then correspond to a classical gauge field and to a quantum gauge field. Yeah? If I only had a U1 classical symmetry, I could not even formulate a meaningful Keldysh theory for this response, because a Keldysh theory always needs a classical and a quantum variable. Yeah? It needs an observable and a response field. So with just this U1 classical, I would not be able to formulate a response theory that is somehow a dynamical response theory for this problem.
Makes sense. Yeah, thank you.
So it's really, so the kind of the conservation laws are absolutely crucial. And again, we can say for a Hamiltonian system, we do not see any difference for this simple argument, yeah, H rho, that's the structure. And quantum symmetries and classical symmetries, they always come in pairs. For the Lindblad, there is this fine print that you can have an open system where particles are lost, or you can have an open system where particle number is conserved. And that's what we are sharpening out here. Yeah, yeah. Ron?
Yeah, regarding what you call spontaneous symmetry breaking in the strong case.
Yeah.
This has nothing to do with the phase transition, right? Like you just mean
no.
You just mean thermalization, right? So
it's the breaking of the that's another very good question. Yeah? So the breaking of this strong symmetry is also something that happens in the process of thermalization. Yeah. So, for example, if you take just an interaction term of a Hamiltonian, yeah, so then it's this structure. So that's the two-body interactions of a Hamiltonian. And then we can have this, right? So that would be the Keldysh representation of an interaction term on the Keldysh contour. Agreed?
Yep.
And then if we go into second order, and you see there is no coupling between these two contours. However, when I go to second order perturbation theory, yeah, I can combine these two vertices, yeah, and I can, for example, find a contraction of this guy with this guy, and say these guys together and these guys together. Yeah? So that gives me a contraction which leaves in the end a term alive. So that's what is contracted. So I minus. Yeah? So you can see at second order perturbation theory, I can construct terms which really look like terms in the Lindblad equation, where terms come from the left and the right onto the density matrix. Yeah? And that is exactly this kind of, that's a signature of thermalization, yeah, in this language. In the sense of onset of dissipation. Okay?
Yes, but I guess maybe it's a little bit different than how I understand this strong symmetry, because let's suppose you have a phase transition. Yeah. Let's suppose you have a system with a strong symmetry that has also a phase transition.
Yeah.
Then and you have a spontaneous symmetry breaking. But now you have this kind of two very different spontaneous symmetry breakings. One associated with this thermalization.
I mean, let me say it like that. So I don't see the strong symmetry, it will get broken, yeah, and what it means in the most general term that I can formulate for that is that you get the onset of irreversible hydrodynamics. Yeah? So that is the statement. Yeah. So you can have so maybe if you have a Hamiltonian system, you have some reversible hydrodynamics, yeah, some sound mode that propagates through the system because particle number and momentum are simultaneously conserved, and you get sound modes. And that's a reversible hydrodynamics. This spontaneous breaking of the quantum symmetry will introduce into your hydrodynamic equations some irreversibility element, yeah, and that's how and that then is in the Keldysh action a signature that will surface as a spontaneous breakdown of this U1 quantum symmetry. But that is not associated to phase transitions also. Yeah? So that's really more in the direction of the system thermalizes, the system acquires irreversibility because it acts as its own bath. That's how I would rank that. But I don't see that really connected to spontaneous breakdown of this U1 quantum symmetry. I don't see it connected to phase transitions. Does this help a bit, or?
Maybe we can discuss later.
We can discuss it later on. Yeah, so,
okay, yeah, thanks.
Sure. Canon, you have a question?
Yeah, I'm wondering whether the edge states play any role in this, or is this inherently a bulk response?
Okay, very, very good question. That is also coming somewhere. So the statement is, yeah, so maybe I go to a slide, to this slide here. So that's actually a bit the summary of this. Yeah, so we extract by calculation and alternatively, which I won't cover, by pure symmetry arguments, we extract this really Chern-Simons action term by integrating out the microscopic fermions, which have a dissipative gap. Yeah? And once you see such an action, which is reversible, which doesn't have any dissipation in it, you immediately conclude there is a bulk boundary correspondence. Yeah? So the bulk boundary correspondence comes about because you confine this problem here, or you confine your physical problem to you subject it to a spatial boundary, say here. So here is insulator, topological insulator, and here is vacuum. Yeah. And whenever you do this construction for such a low energy action problem, you immediately get boundary modes. And that's why I started with this. Yeah? Somehow you can say now, okay, nice, we get this Chern-Simons action out of the calculation or based on symmetry consideration. But even operationally, it gives you the statement that there must be chiral edge modes propagating on top of this purely dissipative insulator, simply because of the bulk boundary correspondence that you can apply whenever you see such a low energy action. All the contribution was mainly to really calculate this low energy effective action and to convince oneself that it comes out. Yeah. So in that sense, yes. Also based on this logic flow, also this dissipative and out of equilibrium systems, they are characterized by propagating chiral edge modes. Yeah. And we can even qualify a bit what the corrections are, but again, protected by symmetries, especially by this U1 quantum symmetry, all corrections, dissipative corrections to this propagating chiral edge modes are subleading in terms of their power counting. So they have a little broadening, but that broadening goes to zero faster with momentum than, so to say, the propagating front that it describes.
Good, thank you.
Okay. So that's really the nice point about this integrating out logic. Yeah. So that's enough, yeah, to be sure that there's chiral edge modes in the game.
Is there any constraint on the dissipative gap that it has to be bigger than something, or can it be any arbitrary gap?
Well, I mean, so the gap in this problem, it comes out, so to say, again, as a kind of result of the calculation. We can relate it to the microscopic quantities. The gap question is somehow more interesting. You have to compare it to something. Yeah? So, and in a problem, yeah, where we only have these Lindblad operators that hammer us into one state, there is nothing to compare to. However, if I would now add a little perturbation, something that I don't control well in my system, yeah, then I would have to, I could compare the energy scale from the perturbation to this dissipative gap. And whenever this gap is really much bigger than this perturbative scale, then I'm on the safe side. Yeah? Likewise, it gives you kind of a rough criterion, for example, also how strongly can your gauge fields, yeah, your external gauge fields with which you probe the system, how strongly can you vary them in space? Yeah? And of course, this variation has to be really very slow on the typical microscopic scales of the system. And so the gap, in other words, is a microscopically determined scale, and you should not, of course, apply magnetic fields or electric fields that are so rapidly oscillating on the lattice scale, and then you're out of game. That's not what this low energy theory describes. So this low energy, integrate out the high energy or high frequency stuff, and then content yourself with this low energy theory. Okay. Are there further questions? Yeah, it's really great that you're not giving up. Really, really a lot of fun. So if not, then I would actually now make really quite a jump ahead. I think these, we also especially in the discussion, came across, I hope, the points that I really wanted to make. Now, I would like to connect to the subject of, it's again about symmetry and open systems, but a very different kind of symmetry. So far, we were really looking at this U1 global phase rotation symmetry. And now I would like to go to the symmetries that allow us to topologically classify open system dynamics, for example. So what I really have in mind here is noted here. So let's, and that will actually also connect me to this discussion on non-Hermitian topology. That's actually currently quite a business. Okay, so let's think about classification of open quantum systems. It will target both equilibrium open systems and non-equilibrium open systems. And so, but even one step before. So let's look at a physical setting where I have a free system, for which I have a Hamiltonian, that I can. So that's just the background of this, and then we'll go to Lindblad in a second. So that I can write in this way, AI, HI, J, AJ. So that's a free system. I have a matrix representation. Free means I have only up to quadratic order in this fermion operators here. Now, what does one have in the closed system case? Well, the object that one classifies in this symmetry classification are actually really nothing but these Hermitian matrices that appear here. So they have this hermiticity property, and you let them undergo. Now comes what we mean by symmetry in this context here. Symmetry operations, which are these very elementary ones, non-spatial and also not necessarily unitary. Namely, we have time reversal, we have charge conjugation, and we have what is called this chiral symmetry, which is nothing but the concatenation of these two guys. Okay, so with from these symmetry operations, I'm pretty sure you've heard that. So you get as a result, you can any matrix that generates a closed system evolution here by a Hermitian Hamiltonian can be ordered into one of 10 symmetry classes, and these are these famous Altland-Zernbauer symmetry classes. And this has really seen, so that's another element that I would like to emphasize. That is essentially classifying symmetries. And later it has been realized in these works here that this also allows you to classify the systems topologically. So all topological insulators or superconductors come to lie in one of these classes, and the distinct advantage is that when you know the class, you can make a lot of physically important statements like which kind of edge modes are present in the system. So that is a bit the mindset. Okay, now what is known about open systems? There people started to look at classifying, instead of the Hermitian matrices Hamiltonian, non-Hermitian matrices, that you can always write as the sum of a Hermitian matrix times I times another Hermitian matrix. So both these guys are Hermitian, but they don't have to commute or anything. So these are just generic non-Hermitian matrices. Now again, you can play the operations of time reversal, charge conjugation, and chiral symmetry, but because the matrix K is not the same as K dagger, yeah, you can also introduce these conjugate variants of the symmetries, yeah, by an additional operation called eta, oftentimes, that take these transformations to another transformation. So this would be just T concatenated with this eta transformation, which does nothing but Hermitian conjugation on this matrix. Okay, and there, if you do this, then you get actually a vastly enlarged number of 38 symmetry classes. Yeah? And that was really shown in these works here. Now, however, there are a few things that are not entirely obvious in this. Yeah? So, for example, what actually is really the physical interpretation of this non-Hermitian matrix? Yeah? Is it now, for example, we had these, we had in our Keldysh framework, we had this spectral Green's function, we had this Keldysh Green's function. So where in these Green's function does, what is actually meant with this matrix really? And it's not always really clearly specified. Then, if I just have a matrix, I cannot really be, I cannot tell you, yeah, what is actually the particle statistics of the particles that are underlying. Yeah? For example, if I write something like that, a j dagger, yeah? So that's a quadratic form, and I only know this matrix. I did not yet specify what's actually these guys. Are these bosons or fermions? Yeah? Then the other issue, yeah? So we talked about the complete positivity of the Lindblad map, yeah, which is at least a consistent open system description. And in these metrics here, if you just talk about matrices, there's no specific constraint on these matrices. Yeah? So the issue of complete positivity or probability conservation is also not completely clear, and also how that would generalize to interacting systems. So the goal of what I want to present here is to do something more from first principles, to start from a consistent Lindblad evolution of these systems, and then think about how from scratch we can develop a classification scheme for these. And then in the end, it should come out, yeah, what are the allowed transformation rules for matrices. Yeah? So we are going somewhat bottom up, starting from the Lindblad or general evolution. And then finally, the result should be, it should tell me something about the matrices instead of saying, okay, I define additional transformations. Okay, so, and now how can one do that? Yeah. So the starting point of this construction is to do symmetry operations in the space where our states are actually defined. Yeah? So, and the arena for say a fermionic system, we look at fermions really to begin with. The arena where fermions are living in is what is called Fock space, and so that is the description of the state, and that's just here one point in this Fock space that describes a fermionic state. Okay, and this is in the formulation of this second quantization is specified by the algebra of the fermionic creation and annihilation operators, which lives on lattice heights I, say. Yeah? So with these operators, we can span the entire Fock space for this problem. They provide a basis for that. Yeah? And then it is also then very well defined what these operations are. For example, time reversal is defined as a transformation that acts on this basis operators here in terms of a unitary matrix. So all it does is to do a unitary transformation on this basis operators AI and also on the Hermitian conjugates, on the AI dagger, and it takes what is called anti-unitary transformation, namely every I that you see in your generator of dynamics, for example, that is sent to -I. That's what time reversal is. And then you have two more operations. You have what is called charge conjugation that sends up to a unitary transformation the operator to its Hermitian conjugate, but it leaves the I intact. And then we have this chiral symmetry, which is nothing but the combination of these two, or the concatenation of these symmetries, which sends operators modulo unitary to Hermitian conjugates and I to minus I. And that's it. That's the kind of elementary transformations that you can do in Fock space. Now, we need to specify the principle of classification. Yeah? So if you speak about a symmetry, yeah, you would have to specify what is actually really left invariant under this symmetry operation. And to this end, from my view, the only way is to look at the essentially equation of motion that the system is undergoing. Yeah? And now we have, for example, these two choices. We can look at equilibrium unitary or unitary evolution. Then the equation of the motion for the system is this one. Yeah? So that's this von Neumann equation. Or if we want a non-equilibrium irreversible evolution, then we can take, for example, this Lindblad equation as a kind of good description for that. So in this way, we can, so to say, cover by these cases, we can cover both the equilibrium and the non-equilibrium world. Okay, so the object of so the physical principle behind the classification here is the invariance of the equation of motion, and we cover both the equilibrium case and the non-equilibrium case. Yeah? And so what this tells us is that the object of classification that we are actually studying is really the generator of dynamics. Yeah? So we have to act somehow on the right-hand side of these equations to define or to see under which operation is this equation invariant. And one thing as a side comment, when we know how the generator of dynamics transforms under this symmetry transformation, it gives us immediately, so to say, the rules how the stationary state would transform under these symmetry operations. But keep in mind really that there is now a huge difference between this equilibrium case and the non-equilibrium case, really in the spirit of what we said before. Yeah? So in the equilibrium case, we have essentially only a Hamiltonian generator of dynamics, which can maybe do self-thermalization. But in the non-equilibrium case, we have many more complicated and many more scales in the problem. Okay, so here are the results of this investigation. So when it comes to states, we find indeed there is only 10 classes, just as for equilibrium ground states, and that is completely independent of the dynamics that is stabilizing it. Yeah, so the second result, yeah, and I want to explain all these results, that's now a kind of a surprise. There is a fundamental distinction between equilibrium and non-equilibrium dynamics. Yeah? And so it picks up this file that we discussed previously. Yeah? So we have two logical options for where the important difference is. One logical option is the big difference is this one here, whether the evolution of the system is unitary or whether it is irreversible. Yeah? Then you would have this unitary dynamics here set apart from irreversible evolution, but irreversible can be irreversible equilibrium or irreversible non-equilibrium, as we said. Yeah? But it turns out that the choice that physics makes is that the unitary dynamics and the irreversible equilibrium dynamics, they are, so to say, in the same dynamical, they obey the same dynamical classification, but the irreversible non-equilibrium classification obeys a completely different rule set of transformation laws that are absolutely not compatible with equilibrium transformation laws. Yeah, so, and that has really important implications. Yeah, this incompatibility. Namely, we get different transformation rules. So it's not only that one cannot really microscopically justify this non-Hermitian classification, but even we get completely different rules how the objects that are making up the dynamics are transforming. Yeah? And we can also see that this matrix classification that was predicted previously is not really robust against the presence of interactions. So let me go to the origin of this, what could be called dynamical fine structure. Yeah? So the statement that equilibrium and non-equilibrium systems are sitting in different and incompatible symmetry classes. Yeah? And that comes, the origin of this fine structure here comes really down to thinking about what is actually time reversal in quantum mechanics. Yeah? So one has to note that it's a combined transformation. Yeah? So there is this static component to time reversal that we already pointed out. Yeah? Namely, that's this part, that's the Fock space part in the transformation. But there's also, of course, in time reversal, there's also a dynamical component. Namely, we send t to minus t in to keep the Schrödinger equation invariant, or alternatively also to keep the von Neumann equation invariant. Yeah? So you have to do this Fock space transformation, and in order to keep the equation invariant, yeah, it's essentially this change in the sign of I that is prescribed by the Fock space part of the transformation that requires us to send t to minus t to finally keep this equation invariant. Yeah. So upshot is time reversal has a Fock space part and a dynamical part. So that is written out here. Time reversal is an action in Fock space, this part, and it is an action on the time coordinate. Yeah? And time in quantum mechanics is not anything that has to do with Fock space. That's really more a parameter with which we run the system through Fock space. Yeah? And it's really important to see this concatenated nature of a full quantum mechanical time reversal transformation, which in particular involves this piece of playing the movie backwards. Yeah? So we are really reversing time to minus t.
Sorry, here we're talking about the. Sorry, question. Here we're talking about the non-Hermitian cases, or because for non-Hermitian cases, I don't know, because you can define two ways time reversal symmetry, right? You can define it either with the conjugation or transpose.
That is no. Here we are at the moment I'm discussing time reversal in quantum mechanics, and I want to arrive at this picture here.
Oh, okay. So this is
okay. And then I mean, so the logic of this approach is really okay. Let's first think about what are symmetries in physics. Yeah. So what are these transformations? Yeah. This T transformation. What is meant with this? Mm-hmm. And it's very basic, but it's also extremely important to realize that it's operation in Fock space and on this parameter T. Yeah? And in our approach, we want in the end to get our transformation rules, yeah, based on this invariance of the equation of motion principle. And then in the last step, we can then say, okay, what does this have to do with, say, this eta transformation, or with this T and T dagger? Yeah? But this should come out of the analysis. We don't want to put this in, because the way to declare the symmetry operations is really if you go to a textbook. Yeah, so then it is okay. Let's first think about Fock space, then think about dynamics, and then think about how the symmetry is represented on some matrices. Yeah? And when you do this non-emission game, then you start with a matrix and you say, okay, I want to assume the same transformations that are familiar from Hamiltonian ground states also apply here. Then you realize, okay, there's this twofold choice, but we would like to rather distill this out of a more elementary consideration. Okay. So, and then you don't run into the trouble. What is this? This is really well defined in Fock space.
Sure. Yeah.
Okay. So quantum mechanical time reversal is declared in this way, but you can, of course, it's not a meaningful thing to do. Yeah, this playing the movie backwards is something that is only meaningful when the dynamics is unitary. Yeah, so when your evolution operator is of this type here, then you can reverse the movie by sending t to minus t, which means so then that u is going to u dagger. Yeah? That is reversing the movie, and that ceases to make sense in the moment that you have any kind of irreversible dynamics, which could, for example, come from self-thermalization or from a coupling to a bath. So we seem to be in some trouble because it looks like we cannot extend this concept of time reversal to the situation where you have some irreversibility involved, right? But it comes to aid now what we learned previously, namely, it turns out that you can formulate what we deem then what we call thermal time reversal, yeah, which is not only the concatenation of this Fock space transformation T, which is defined here, but also is a slightly extended variant of this transformation T to minus T, namely by sending T to minus T and doing the slight shift into the complex plane of time. Yeah? And it turns out that this transformation is really the right way of declaring time reversal symmetry, or just a thermal time reversal, yeah, to still see that a system can be to keep it invariant under this transformation. And so this is the proper generalization from unitary to the entire set of dynamics, which is irreversible equilibrium dynamics. Okay, so that's what you can do in equilibrium dynamics. But out of equilibrium, yeah, there is really no way of extending the T to minus T transformation that one has for unitary dynamics. Yeah? And therefore, if you want to represent the full time reversal transformation out of equilibrium, then it will be the operation T times doing nothing. Yeah? T is sent to plus T, and then you have to see, okay, can you still have the equation of motion invariant under this transformation? Yeah? And that is really that is demonstrating that the watershed between symmetry classes is in or out of equilibrium dynamics and not unitary or irreversible dynamics. Yes, Canon?
Yeah, sorry, I think you mentioned it in the previous lecture that this I beta, does it correspond to shifting the contour? So you're moving from one contour that goes from one direction in time to another that flows in reverse in time. Can I understand it this way?
It's more like a, I mean, if we say, okay, time is running here, so like that, yeah. So and that's initial and final state, yeah. So then it's actually, so if this is a real axis, then it's more something like it looks like that, yeah. So it's an version in the complex time plane.
So I'm not actually shifting from one contour.
No, it's not mixing the two contours.
Okay, I see.
It's diagonal in the contour space. Yeah?
I see.
Some more question?
And can I conclude that, like, I would need this beta to be 0 in unitary dynamics, but in irreversible equilibrium it has to be non-zero? Is that the case?
It's, well, I mean, that's a bit, I mean, I would view this as a one parameter freedom that you have that physically associates to the energy density that your problem has. So, and yeah, I mean the limits beta equals 0, beta equals infinity, they are somehow a little artificial anyways. Yeah, and I would always look at it like, I mean, take this beta for the sake of thinking about it finite. Yeah, and then that's what you should have. Yeah? So formally, of course, if you're asking that, the unitary case formally is of course covered by just taking beta to 0. Yeah? And so this kind of equation that we had previously, so dt rho I h commutator rho, this equation is of course invariant under take any beta, and it will be invariant. Yeah? Or more precisely, the Keldysh path integral formulation for this is invariant under any beta, but so to say, not only beta equals formally 0, yeah? But even more, any beta. That's, I think, yeah. Okay, further?
So this kind of looks like what we had in the last lecture, this symmetry of the Keldysh action under the discrete transformation. Are those, what is the exact relationship between these two?
It is really, it is the same thing. So I mean, that's why I wanted to, I mean, to really have an application of this in the lecture. Yeah. So, I mean, it's here. So what we had previously, yeah. So we looked essentially at fields psi plus minus, yeah, and of t, they would go into psi plus minus minus t plus I beta, right? That's what we had previously. What I'm saying now is essentially, well, but this field could come with some additional freedom I, yeah, for example, a lattice side, yeah, and so then you see, okay, now we can be a bit more general than for this single degree of freedom that we looked at previously, but we can actually look at a complete bunch of them. Yeah? And so we are looking at something more general than previously, if you like. Yeah? And that's really, I think that's the most, that also gives us a more interpretation of this symmetry. Yeah, previously I was essentially focusing on how would this argument here transform, that, so that was focusing essentially on this part here of the transformation, while now we learned, okay, there is also this kind of Fock-based part, yeah, that acts on the on these external indices of these field operators or of the fields on the Keldysh contour. Okay. More questions? Okay. Good. So now we can come to, so that is all completely general. Yeah? So we have this equation of motion. We did not specify whether these are interacting or non-interacting systems. That just specifies the principles of this classification and nails down a difference between equilibrium and non-equilibrium. Now, to finally connect, or to connect it to this matrix classification of non-Hermitian topology, yeah, we look at the special class of these Lindblad generators, which are Gaussian. Yeah? So meaning that the Hamiltonian is only some quadratic object, so that I can characterize it by this matrix H. Yeah? And note that I've introduced here some, I've doubled essentially I've just rewritten this thing in what is called number space. And so I collect together A and A dagger operators to give it a bigger vector. So I can also describe systems with superconductivity or so. And similarly, we want also the Lindblad operators to be quadratic forms. Yeah, so or more precisely what I mean, yeah, so this L dagger L here should take the form of a quadratic form, and the Lindblad operators that stand here are just the superposition of linear in fermion and creation and annihilation operators. So that this entire equation becomes a quadratic equation in the creation and annihilation operators. Okay. So now there are some constraints on these matrices that you find. So the important point here is I can characterize the entire Lindblad evolution then in terms of one matrix H, which sandwiches this quadratic form in the Hamiltonian. And I have two matrices, two Hermitian matrices again, which together give a non-Hermitian matrix, D and P, which characterize for me the dissipation, the dissipative evolution. So I end up with three matrices, which are then ready somehow to pick up the transformation laws of a non-Hermitian matrix classification. And I invite everyone to check, for example, these relations, if these relations are, that they're really fulfilled. Now we can do the translation table again, that we learned yesterday, and map this quadratic Lindblad equation into a Keldysh functional integral. It will also be kind of a simple structure, namely the action will be quadratic in these fields entirely. And then you see, oh, where do these matrices here appear? H, D, and P. They take a pretty neat form, I would say, namely this matrix P that is showing up, that shows up in the noise component, or in this, this is the P, what we call P in the as a matrix here. And then the matrix K is here Hamiltonian minus this damping matrix D. So there's a non-Hermitian spectral matrix K that's showing up here. So recall, this here is the inverse retarded Green's function. And what stands here? This is the inverse advanced, and this is this noise component. And now you see how do these matrices in the Lindblad equation morph into the Keldysh language. Okay, this formulation here is also able, of course, to cover the case of thermal equilibrium, in which case we have here fluctuation dissipation theorem, which tells us the presence of the thermal symmetry forces a relation between the matrix D, which enters here in the retarded advanced Green's function, and the matrix P, which stands here in this fluctuation component. So that's now a way of, in very simple terms, parametrizing both a paradigmatic equilibrium situation, or just equilibrium situation for a Gaussian quadratic theory on the one hand, and also non-equilibrium conditions in the spirit of this Lindblad equation by just a different regime for these matrices. Okay, now how can we characterize the steady state of this problem here? Well, the steady state is nothing dynamical, that you can express it, for example, as a trace over the density matrix of the stationary state. And the information on this Gaussian system is entirely encoded in what is called covariance matrix. So it's just essentially A, B dagger, minus, and the commutator of that. That encodes the non-trivial information. The anti-commutator for fermions is just unity and thereby trivial. Okay, and in the Keldysh language, so the covariance matrix, you can reconstruct it in this way. So that's from the Keldysh Green's function frequency integral over the Keldysh Green's function, equal time Keldysh Green's function. Okay, now we already come to one important point, that there's not only a single gap in these Gaussian evolutions, but there's actually two gaps that both have to be non-vanishing in order to represent a stable physical situation. And the two gaps, they are associated to a gap in this matrix here and a gap in this matrix. So how does this come about? So now I want to demonstrate how this works. How do these two gaps come about? So let's first think about this, what is called spectral gap. So that's the gap in this function k omega, part of the retarded response. So what is meant with this here is a situation that we always stay away from the zero in the complex frequency plane. So here, when I plot the poles of the retarded Green's function. So this is the inverse retarded Green's function. So the poles are where this object here equals 0. Yeah? So for example, if you have just a Hamiltonian system, then the poles are just the eigenvalues of the Hamiltonian. Recall this is just this is in the, if we have no dissipation, then we just have a Hamiltonian, and then the poles are just lying near the real axis here. Yeah? If we have a purely dissipative situation, so we have only I, the omega, then all the poles would concentrate here on the imaginary axis. And when we have a competition of these, then the poles are somewhere in the complex plane. Yeah. And the definition of the spectral gap is that we really always stay away from this 0. Yeah? So whenever, for example, the Hamiltonian gap is this distance here, if the energies go to 0, then the gap closes, then these two guys here would touch each other. That's the gap closing, spectral gap closing. If in our dissipative system, the damping gap goes to 0, then we would approach this point here coming from the purely imaginary axis. Okay, but then there is a second important gap, which operationally is defined as the purity gap. And these are the 0 modes of this covariance matrix. Yeah? So encoding all the static information of the Gaussian problem. Okay? So this is a Hermitian matrix. You can check that this is a Hermitian matrix here. And the purity gap is defined as this object not having any 0 eigenvalues. Yeah? So similar to a Hamiltonian, to a gap of a Hamiltonian, where this Hamiltonian is a Hermitian matrix that shouldn't have 0 eigenvalues, we require for this purity gap the covariance matrix not to have 0 eigenvalues. Yeah? And you can see that if you work in a parametrization of the stationary state, and that is written like this. Yeah? It's always possible because we have a Gaussian system, so we can encode all the information in some matrix theta, Hermitian matrix theta, and then you see, okay, I can evaluate it to this form. So this tanh function is somehow this function, and a purity gap means that we're always staying away from, so to say, the 0 of this tanh function. So that's a purity gap. And let's take an example. Yeah, when for a purity gap in equilibrium, clearly this H, this theta, what stands here is nothing but beta times this H matrix. And we get a purity gap closing either when the Hamiltonian itself has 0 modes. Yeah? So if the spectral gap is closed, or at infinite temperature where beta is 0. Yeah? So, and so that would be a purity gap. So if your state in the upshot is too strongly mixed, so you have an infinite temperature state, then the purity gap would be closed. Yeah? So if we have a spectral gap in the problem, then we can one can show that the presence of this purity gap is equivalent to having no 0 modes in this matrix P that stands here. Yeah? So now what we've shown, we have 2 gaps. One is a gap in this matrix here, and one is a gap in this matrix here. Okay. So that is, so to say, that is explaining under which conditions is this classification that we're formulating here is actually robust. Yeah? So you need 2 gaps to be present. If they are present, then you can be sure that your classification is robust. Okay, let me now come to this point here. So we want to clarify, or we want to say that the anti-unitary symmetries, yeah, so those that involve time reversal, or so those that that send I to minus I. Yeah? So these are these anti-unitary symmetries. Yeah? And when we run our program and realize that in equilibrium we have t to minus t plus I beta as a representation of time reversal in we have this as a representation of time reversal, and here we have t to plus t in the non-equilibrium case. Then we get here, for the anti-unitary symmetries, we get here different rules for the transformation behavior of the Hamiltonian matrix entering our action. I see some question here. Is there some question? No?
So Sebastian, we're getting pretty close to the end.
Yeah. Okay. I'm coming.
It may be good to try to. Okay.
Yeah. Okay. Right. So So all these transformations in which are anti-unitary, so time reversal and this chiral symmetry, they produce out of equilibrium different rules for the transformation of this Hamiltonian matrix. Yeah? And that comes to the counting of how many dynamical symmetry classes are there in nature. So we count it as 3 plus 7 plus 7, where these numbers come about in 3 classes. There is no anti-unitary symmetries involved. That's this one, this one, this one. So there's absolutely no anti-unitary symmetries involved. So therefore, there is no difference between this equilibrium transformation and the non-equilibrium transformation. In 7 classes, all that are marked here in red, namely 6 with time reversal and 1 with chiral symmetry, there we have now the anti-unitary symmetry represented like this, the dynamical part of it. And in 7 classes, out of equilibrium, we have this realization of time reversal in the time domain. And that makes up this 3 plus 7 plus 7, so in total 17 dynamical classes. And okay, I still have here an example. Maybe I go through it. Yeah, so that's something really where it comes out clearly. So this different representation of anti-unitary symmetries, we can look at a problem that is characterized by a covariance matrix. Yeah, so that characterizes the steady state of the problem for a 2-band model. This is the vector of Pauli matrices, and this here encodes the information about the state. Yeah, so that's a 2x2 Hermitian covariance matrix. Yeah. Now we look for one of the anti-unitary symmetries, namely chiral symmetry, and chiral symmetry is on the state of the covariance matrix. It's represented, or it's this condition on the covariance matrix. When we have this chiral symmetry present, then it's known that you can topologically characterize these states by a winding number. Yeah? So, and that's illustrated here. So this sphere is where this vector n of k can lie. Yeah? And you have a non-trivial winding number whenever you go once across your Brion zone, so from k to, or from minus pi to plus pi, which is the same point. When you do this in your base manifold, and then your vector n of k has revolved once around in the target manifold, and so in this mapping, then you have a non-trivial winding number. So that's how these chiral states are characterized topologically. Yeah? Okay, now in equilibrium, this vector is given by this object here, and note that we can also include finite temperature states in this problem. Yeah, as long as the purity gap is open, it's in the stable. It's stable in the sense of our classification, as long as beta is not 0, so which would mean a purity gap closing here. Then this is this vector n of k, and you see indeed this is the rule that we look up here. Yeah, for the equilibrium Hamiltonian case, together with this minus sign, this is the rule that the Hamiltonian should obey in equilibrium under a chiral symmetry. So that means that the Hamiltonian here, yeah, you can see it is proportional to this vector nk, so it lies really in the xy plane. Okay, let's look at the same situation now out of equilibrium. And we found an example where we take again an engineered dissipative dynamics which pushes us into such a chiral state. And then we switch on a Hamiltonian on top of that, on top of this engineered dissipative dynamics. And now this table here tells us that the transformation rule has to come with this minus sign, which together with this gives us this transformation of the Hamiltonian. So that means that the Hamiltonian should now not anti-commute with this unitary, but rather commute with it. So that means it must point in the z direction. So I think this example points out clearly that if we want to stabilize one and the same stationary state, or one stationary state in the same dynamic, in the same symmetry class, then the transformation rule of the Hamiltonian contribution to the total generator of dynamics, the Hamiltonian rule of transformation can be extremely different. Yeah? Namely, once the Hamiltonian has to lie here in plane, and once it has to lie out of plane in the out of equilibrium context. Okay, with this, I think I should indeed come to a conclusion of this, unfortunately, lecture 2 that I did. And I think take-home messages can be this one. We have encountered an example of dynamical universality, where somehow topology is able to beat dynamics, yeah, in the sense that this Bazin of attraction, or the domain of attraction for this topological field theory that we constructed, is not limited to equilibrium or to equilibrium dynamics, but likewise can show up in a non-equilibrium dynamics. So topology is really seems to be stronger. It's a bit philosophical, but seems to be stronger, can dominate over the dynamics in this problem. While when it comes to symmetry classification, we found somehow the opposite phenomenon. Namely, we realized that there's really a dynamical fine structure that shows up, yeah, when you want to classify the generators of dynamics. So for the state, there is just 10 classes, and these are the well-known Altland-Zirnbauer classes. But when it comes to dynamics, there's really a fundamental distinction between equilibrium and non-equilibrium dynamics, which results in a total of 17 dynamical symmetry classes, with the interesting or ingredient, or with the, I think, really important point, yeah, that the watershed is between equilibrium and non-equilibrium, and not somehow reversible versus irreversible. So with this, I thank you very much for your attention, and I'm happy to take some more questions. I see one by Sarah. Please.
Hi. So my question is, at some point you told us some other studies said that like 38 classes.
Yeah.
And now here we see that 17. So how to see that discrepancy, or is there maybe no discrepancy? Maybe I'm missing something.
No. That's a very good point. Yeah, I mean, so the initial goal, yeah, of this study was somehow to reproduce this 38 classes from a maybe a bit more fundamentalistic point of view, yeah, namely starting from how would you think about symmetries, yeah, so, and that starts somehow in the second quantization in Fock space, yeah. And we thought maybe in the end then these 38 classes come out, and this eta operation, yeah, so sending matrices to their Hermitian conjugates, that should somehow come out, yeah. But then, okay, so in the course of this analysis, yeah, we learned that somehow, I mean, at least you could not derive these transformation laws from first principles, and moreover, yeah, so even it goes as far as So what this classification does is to say, okay, I know the transformation rules of Altland and Zirnbauer, and I just copy them over to the non-Hermitian world. Yeah? Now, what we see, even these operation, even the representation of the symmetry is a different one. Yeah? So we actually don't have the same rules that symmetries act on these matrices when we take seriously this approach of starting in Fock space and then thinking about invariance of the equation of motion. Yeah? So it's really, I think, yeah, and we also understand that it's not really, so this classification is not really stable under perturbations. Yeah, that's somehow this argument here. So the argument is, so whenever you try, you just try to classify the symmetry in terms of only two matrices. Yeah. As a one non-Hermitian matrix, say H and D. So two Hermitian matrices combining into a non-Hermitian one. The question you can ask is, can you at all, even conceptually, define a stable classification? Yeah? So discarding this third matrix, which is necessary by trace preservation and everything we discussed in the very beginning. And then the answer is, unfortunately, it's not possible. Yeah? Because whenever you you have an interacting problem and you do perturbation theory, yeah, then you can get a self energy, yeah, for example, yeah, which depends on all these three generators. Yeah, so, and if this here, this non-Hermitian matrix is in some symmetry class, but this one breaks explicitly some of the symmetries, you would be completely misled by analyzing the symmetries of this guy alone, because in first order perturbation theory, looking at this diagram here, you would already get somehow a violation of the symmetry. So, and that's also not good for a symmetry classification, yeah, when it's not robust under, so to say, perturbation theory, or more physically speaking, if it's not robust on under how you look at your system, yeah, if you do your perturbation theory or not. Yeah. And that's also a problem here. Yeah? So I would even say it's fundamentally not possible in an open system, or in a driven open system, to restrict your attention to two matrices, or to two Hermitian or one non-Hermitian matrix, because of the arguments I gave. The good news is, if you have an open system that is in equilibrium, yeah, then it works. But that's again protected, yeah, because P and D are not independent; they are rather related by this this fluctuation dissipation relation.
Thank you for your insight.
Yeah, it is very welcome. Yeah. So Syed.
Yes. So I think I just want to follow this, because what you're really doing in the non-equilibrium case is that you're applying the same representation of the typical Hermitian system to the bunch of three other Hermitian matrices, right? Because H, D, and P are all Hermitian by themselves. Is that correct?
Yeah.
So you're not really using this conjugate transpose thing that people use for non-Hermitian classification, which is going to end up with 38 classes. So you're still using the time reversal symmetry as the way that people define time reversal symmetry for Hermitian system.
Yeah. But so I would then ask back, what is the justification, yeah, of imposing the transformation rule of this matrix? What is the justification? Yeah, and if you confine yourself to closed systems, yeah, then the justification is as follows: take your Hamiltonian, take your Schrödinger equation, and look when is it invariant, yeah, and do this, yeah, by applying a Fock space transformation on your field operators and t to minus t, yeah, and then you produce the rule of transformation for the matrix, Yeah. So maybe it's this argument. Yeah. So AI, and then I put some like this. Yeah. So what I'm doing when I'm doing this transformation is I'm doing U, A, J, and a U dagger I, okay, and then and then let's say we want to look at time reversal. So time reversal, every complex number is conjugated. Yeah, so I should copy this here, and then you do the brackets in the other way. Yeah, so then you say, okay, AI U dagger H star U IJ AJ. That is now the condition for time reversal is that the original operator and the transformed are the same. And from that, you then say, okay, the condition is U dagger H star U equals H. Yeah. So, and so that's really a logical way of doing these things. Yeah. And now you can justify why this rule. And if you just take now a non-Hermitian matrix, where does this rule come from? Yeah.
No, I mean, yes, I mean, that's why.
That's the reasoning.
Yeah, yeah.
And I don't see where this comes from when you don't stick to this reasoning. Yeah? So physics is defined in Fock space, as bad as it sounds also to me. But I mean, when it comes to this, yeah, Wigner theorem, what is a symmetry and so on, then I think there is not really much alternative of just saying, okay, I have here this matrix and I want it to, so that's essentially promoting this here now to any kind of non-Hermitian K. Yeah, but that's not really right.
Well, I mean, over the justification, I think comes from the fact that when you have non-Hermitian system, you have complex energy. So those symmetries gonna impose some condition on your imaginary part of the energy, not the real part of the energy.
But then I ask you back, where is this imaginary part coming from? Yeah?
Oh yeah, I mean, yeah, the physical,
and
yeah,
it must come out of something like H plus H system bath plus H bath. Yeah. And I integrate out this path, and that gives me some imaginary parts to the Hamiltonian as we discussed it. Yeah, and then, but then if you go through it, then you come out exactly at what I'm discussing. Yeah, namely, you have to formulate some Lindblad equation or some equilibrium open system. Yeah, but I'm only saying, so that's exactly what we cover. Yeah, and we are
so
then on the safe side by this fundamentalist point of view.
Sure. Then let me ask you a final question. In your example that you show a chiral symmetry, which is if you go to that page, equal to here. So in the non-equilibrium part, you're showing that transformation gives you H. So when H is a Hermitian itself, this is you always can find a trivial identity matrix for US, right?
And this one here?
Yes. And I can always use identity as a...
No. But U as is fixed. No, U as is fixed by this. Yeah. So we want to look at a chiral state to begin with. Yeah. So that's just, I mean, now for the sake of example, I look, what is a chiral symmetry doing? What is it? I look in this table. What is a chiral symmetry doing on a stationary state? When do I have a chiral stationary state? Yeah. And now I'm looking at the chiral transformation realized in this way, and I have already in this way I've already fixed this US. Yeah? So then the statement is it's a non-trivial statement. Yeah. So when this is a sigma z, then H must be proportional sigma z as well, and cannot have anything in the XY plane. Otherwise, that would anti-commute, and that's what happens here. Yeah.
Interesting. Because if it was non-Hermitian, then it would be just pseudo-Hermiticity. But
if you were in this Hermitian, non-Hermitian business, then you would have, I would say, erroneously claimed that the symmetry is realized in exactly the same way as in the Hamiltonian world. But there's this, but I mean, there's not a
that's an interesting insight. Yeah.
And that's also I kind of it's really surprising to me that, I mean, when we speak of a chiral Hamiltonian out of equilibrium, this is what chiral means. Yeah? not this, what you would naively think.
Yeah.
So, but yeah, that's a point of, I mean, that's just, I mean, really surfacing the structure of that we use.
Thank you.
Okay. More questions? Okay. Yeah, so I wanted to say really thank you very much for these great questions all the way. I must say in the last lecture, it's now just approaching 9, and after a day of work with this 3 hours of lecture, I'm somehow getting a bit dizzy. So I think the second one was, sorry for that, but thank you very much for staying with me and for asking this fantastic question. It was a great fun. And I think that I got most of the messages through from my point of view because you asked these great questions. And so it's much better to come to the point when you ask questions than to go through your slides and so on. So thanks a lot. And I want to be available also if you have, I mean, further questions or remarks or whatever on this Discord. Yeah. So, or I mean, I guess you can find my name on the internet. You can always write me an email. So I'm really happy to discuss further things. And yeah, it was a great pleasure. So thanks again.
Thank you. Yeah, that's the questions for the great lectures. So I will close the meeting and we will start at 2 for the next lecture. Okay, bye-bye. Thank you. Thank you very much. Bye.